2 minutes ago, somewhere 25 billion kilometers from Earth, a spacecraft no bigger than a small car was busy doing something nobody specifically programmed it to do back in 1977 when it was built. Building the first continuous map of electron density in interstellar space, one measurement at a time, automatically, quietly, using instruments that were designed for a completely different purpose and that nobody imagined would still be functioning nearly 50 years after launch. Subscribe right now before we go further, because what Voyager 1 has been producing out in the space between the stars is something scientists did not even know was possible until the data was already sitting in the archives waiting to be discovered. Let's set the scene properly, because the context is everything here. Voyager 1 launched on September 5th, 1977 from Cape Canaveral, Florida. Its primary mission was planetary science, a grand tour of the outer solar system, flying past Jupiter in March 1979 and Saturn in November 1980. Capturing close-up images and measurements of those planets and their moons before continuing outward into the deep solar system. By the time Voyager 1 crossed the heliopause on August 25, 2012, at a distance of 121.6 astronomical units from the Sun, it had been traveling for 35 years. The scientists who built it had retired. Some had passed away. The engineers who coded its software had moved on to careers in entirely different fields. And yet the spacecraft kept going, kept transmitting, kept measuring. Right now in 2026, it sits at approximately 167.5 astronomical units from the Sun, roughly 25 billion kilometers from home, and its signal takes over 23 hours to reach Earth, traveling at the speed of light. What Voyager 1 has been inadvertently mapping since its heliopause crossing in 2012 is the electron density of the very local interstellar medium, the specific thin shell of interstellar space immediately surrounding our solar system, out to distances of roughly 46 astronomical units beyond the heliopause. And it has been doing this with an instrument that was never specifically designed to build a continuous density map. It was designed to detect plasma waves triggered by specific events. What nobody fully anticipated was that the instrument would also pick up something far subtler and far more scientifically valuable, a continuous, persistent background signal from the interstellar plasma itself that turns out to encode a running record of exactly how dense the electron environment is, wherever Voyager 1 happens to be at any given moment. The instrument responsible for all of this is the plasma wave system, sometimes called the Plasma Wave Subsystem, or PWS. It consists of 2 hollow fiberglass antenna rods, each about 10 meters long, extending behind the spacecraft. These antennas were originally designed to detect plasma wave events, specific electromagnetic oscillations triggered when energetic events, like solar eruptions, sending shock waves outward through the solar system, drive the surrounding plasma into strong, detectable vibration. The physics behind the measurement is elegant and precise. Plasma oscillates at a specific natural frequency, called the electron plasma frequency, that depends directly on how many electrons are packed into each cubic centimeter of space. The higher the electron density, the higher the oscillation frequency. And since frequency is something Voyager's instrument can measure with high precision, every time the plasma oscillates strongly enough to detect, scientists can calculate the local electron density with remarkable accuracy, simply by reading off the frequency. The problem was that before 2021, the only times Voyager's instrument could make those density measurements were during specific events, when solar activity sent energetic shock waves outward through the heliosphere, hit the heliopause, drove compression waves into the interstellar medium on the other side, and made the surrounding plasma ring strongly enough for the instruments to clearly pick up. These events, which scientists nicknamed tsunamis because of the way they swept through the interstellar medium with enormous energy, occurred roughly once a year at most. Between tsunamis, the plasma data from Voyager was essentially silent on density, leaving long gaps in what scientists could measure. Donald Gurnett, the University of Iowa physicist, who was the principal investigator for the plasma wave system and who spent decades listening to what Voyager sent home, described the result as a picture that was, in his words, kind of sparse. Scientists had isolated data points, not a continuous map. Then in 2021, something changed. Stella Koch-Ocker, a doctoral student in astronomy at Cornell University, working with professors James Cordes and Shami Chatterjee, along with Gurnett and his Iowa colleague William Kurth, went back through years of archived Voyager 1 plasma wave data with fresh eyes and a specific question in mind. Was there anything in the data between the tsunami events and the quiet intervals when no major solar shockwave was sweeping through that could be used for density measurements? What they found, documented in a paper published in Nature Astronomy in May 2021, was something hiding in plain sight. A faint, narrowband, persistent electromagnetic emission from the interstellar plasma itself, present almost continuously in Voyager 1's data from 2017 onward, never going away, never requiring an external trigger to produce it. Not a strong, dramatic signal like the tsunami-triggered events. A subtle, constant hum, sitting just above the instrument's noise floor produced by the interstellar plasma vibrating at its natural frequency, essentially all the time. Ocker described it as very faint and monotone, sitting in a narrow frequency bandwidth. James Cordes used a comparison that people understood immediately. The tsunami events, he said, are like lightning in a thunderstorm. What they had discovered was the quiet, persistent rain in between. NASA's Jet Propulsion Laboratory put it precisely in their official statement about the discovery. They explained that the electron density around Voyager 1 started rising in 2013, just after the heliopause crossing, and reached its then current levels around mid-2015, a roughly 40-fold increase in density compared to what Voyager had measured inside the heliosphere. And critically, JPL noted that those levels persisted through the entire dataset, which at that time ran through early 2020. The hum was always there. The density measurement was always available. Scientists just had not looked at that specific subtle signal before. To understand why having a continuous electron density map of the interstellar medium matters so much, it helps to understand what scientists were working with before Voyager 1 crossed the heliopause. Most of what astronomers knew about the electron density of the interstellar medium before 2012 came from remote observations of distant pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses, and when those pulses travel through the interstellar medium on their way to Earth, the electrons in the interstellar medium slow them down by a predictable amount that depends directly on how many electrons the pulse had to travel through. By measuring how much different frequencies of pulsar radio waves are delayed relative to each other, a quantity scientists call the dispersion measure, astronomers can calculate the average electron density along the line of sight between Earth and each pulsar. This technique has been used for decades to build up maps of the electron density of the Milky Way, and those maps are genuinely impressive achievements of indirect observation. But they have a fundamental limitation. They give averages along entire lines of sight that may stretch thousands of light years, and they smooth out all of the local, small-scale structure in the electron density that varies from one point in space to the next on scales of 1 astronomical unit or less. They tell you the average density of a very long stretch of space, not the density at any specific point along that stretch. Voyager 1's continuous density map is something fundamentally different. It is not an average along a line of sight. It is a direct, local, in situ measurement at one specific point in space, then the next point slightly farther away a few days later, then the next point after that, building up a ground-level view of how the electron density actually varies from one location to the next, inside the interstellar medium at the scale of individual astronomical units. This is the difference between looking at the surface of a lake from a satellite and dragging a physical sensor through the water. The satellite image gives you an enormously wide field of view, but it averages over the surface and cannot see the fine structure beneath. The in-water sensor tells you exactly what is at each specific point, the temperature, the chemistry, the turbulence, with a precision that no remote observation can match. Voyager 1 is the only in-water sensor humanity currently has in the interstellar medium. The electron density values Voyager 1 has measured are worth spelling out precisely because they tell a story on their own. Inside the heliosphere, in the outer heliospheric region just before the heliopause, the electron density was roughly 0.002 electrons per cubic centimeter. When Voyager 1 crossed the heliopause in August 2012, the first plasma oscillation event detected just after the crossing measured a density of about 0.08 electrons per cubic centimeter. That is a factor of 40 higher than the inside, happening essentially instantaneously as Voyager crossed the boundary. The expected range for the interstellar medium based on earlier remote observations was between 0.05 and 0.22 electrons per cubic centimeter. So 0.08 was within the expected range, but toward the lower end. Through 2013, 2014, and into 2015, as Voyager moved deeper into the interstellar medium, the density measurements from subsequent plasma oscillation events showed a gradual upward trend. By mid-2015, according to the JPL analysis, the density had stabilized at a higher value, consistent with Voyager having moved further away from the boundary where the heliopause was compressing and diluting the local interstellar medium. And then the continuous hum, detected from 2017 onward, gave scientists a running record of how this density continued to evolve as Voyager crossed into regions of the interstellar medium that no measurement had ever sampled before. The density was not constant. It showed fluctuations on scales of about 1 astronomical unit, fluctuations that are the signature of turbulence in the interstellar plasma driven by galaxy-scale processes. And according to the PNAS paper that interviewed Gurnett in 2021, the density was still gradually rising toward what he predicted would eventually be a peak before coming back down. possibly because interstellar material is piling up against the outside of the heliopause like snow in front of a slowly moving plow, being compressed by the heliosphere's outward pressure into a slightly denser shell just beyond the boundary. Whether that prediction proves correct will depend entirely on how long Voyager 1's instruments remain operational to keep measuring. The scientific value of what this persistent hum enables is genuinely profound, and NASA made this explicit, and NASA made this explicit. Shami Chatterjee, one of the Cornell co-authors, said directly that this new data provides the most detailed in situ measurements of the interstellar medium ever obtained anywhere. That is not a casual statement. It means that a 49-year-old spacecraft, using a 49-year-old instrument to detect a signal nobody originally designed it to detect, is currently producing measurements of interstellar space that are more detailed and more comprehensive than anything any other instrument has ever produced. Not in competition with better instruments, not second best to something newer, the absolute best, because nothing else is there. And what this continuous map has revealed about the interstellar medium is itself a story worth telling in full, because the picture that has emerged is more complex and more dynamic than most pre-Voyager models predicted. The first thing the continuous density measurements showed was that the density of the very local interstellar medium is not constant. It varies. The electron density rose in 2013, stabilized around 2015, and then showed fluctuations on scales of about 1 astronomical unit. Variations that reveal the presence of turbulence in the interstellar plasma that is being driven not by our sun, but by the large-scale dynamics of the Milky Way galaxy itself. Waves generated by the galaxy's own rotation, ripples spreading outward from supernova explosions hundreds of light years away, pressure gradients that have been building and shifting over millions of years. All of these processes leave traces in the fine structure of the local electron density that Voyager's continuous map can detect. No remote telescope on Earth or in orbit can see this turbulence directly. It can only be detected from inside the interstellar medium by a spacecraft physically present there. The 2023 IOP Science paper by Gurnett, Kurth, and colleagues took this even further, compiling the full sequence of electron density measurements from 2012 through the data available at the time of that paper's writing, creating what amounted to the most detailed timeline ever assembled of how the electron density of the very local interstellar medium varied as Voyager 1 moved through it. That paper identified 8 distinct plasma oscillation events in the Voyager 1 record, each one associated with a specific solar activity episode, and showed that the density values measured during those events traced a gradual upward trend from about 0.08 electrons per cubic centimeter just after the heliopause crossing in 2012, rising to higher values through 2019 as Voyager moved deeper into the local interstellar medium. The paper used these measurements to predict when future shockwaves driven by solar cycle 25, whose maximum was expected around July 2025, would reach Voyager 1 and Voyager 2, applying basic orbital mechanics and plasma physics to show that a solar cycle 25-driven shockwave launched from the Sun at the cycle maximum would reach Voyager 1 in approximately 2036, by which time the spacecraft will be at roughly 208 astronomical units, making it unlikely, though not impossible, that the instruments will still be functioning and able to send data home. The May 2026 Astrophysical Journal paper by Jiwoo Park, Lanjian, Daniel Berdichevsky, Adam Szabo, and Leonard Berlage extended the density record even further, combining the magnetic field data with the electron density measurements in a unified picture covering Voyager 1's observations from 2012 all the way through mid-2025. That paper specifically highlighted the panel of electron density measurements as one of the key datasets in their combined analysis, showing how the density behavior tracked the magnetic field evolution through the magnetic hump of 2020 to 2022 and into the post-hump period that Voyager 1 has been traveling through ever since. The density data and the magnetic field data tell a consistent story, a story of a local interstellar medium that is more layered, more dynamic, and more influenced by our own sun's activity than any model built before Voyager got there had fully captured. Now, let's talk about the extraordinary infrastructure that makes receiving any of this map data possible in the first place. Because the technical challenge of listening to Voyager 1 across 25 billion kilometers is as remarkable as anything the spacecraft has detected. Voyager 1's radio transmitter produces about 22 watts of power, roughly equivalent to a refrigerator light bulb. When that signal leaves the spacecraft's high-gain dish antenna and begins traveling through space, it spreads out in all directions and loses energy with the square of the distance traveled. By the time it crosses 25 billion kilometers and arrives at Earth, the received power is on the order of 1 billion times smaller than what it was when it left the spacecraft. A signal this faint requires the most sensitive radio receivers on Earth just to detect it at all. Those receivers are the 70-meter dish antennas of NASA's Deep Space Network, located in Goldstone, California, Madrid, Spain, and Canberra, Australia, positioned around the globe so that as Earth rotates, at least one of these enormous structures is always oriented toward whatever part of the sky Voyager 1 happens to be in. Even with these dishes, which are among the most sensitive radio receivers ever built, the data rate from Voyager 1 is around 160 bits per second at most. Every density measurement, every magnetic field reading, every plasma wave detection that goes into the interstellar map Voyager has been building since 2012 arrived home through that trickle of a signal, assembled bit by bit across a communication gap that currently exceeds 23 hours one way. The power situation behind that signal is also moving toward a critical threshold. Voyager 1 runs on 3 radioisotope thermoelectric generators loaded with plutonium-238. These generators convert the heat of radioactive decay directly into electricity, and they have been doing so continuously since 1977. At launch, they produced roughly 470 watts. By 2026, after 49 years of steady radioactive decay, they produce less than half that, somewhere around 200 watts or below. To manage the shrinking electrical budget, engineers have been carefully shutting down instruments one by one over the years, trading specific scientific capabilities for the longevity of the instruments that still have the most to offer. The most recent shutdowns were the cosmic ray subsystem in February 2025 and the low-energy charged particles experiment on April 17, 2026, which had operated for 49 unbroken years. What remains active are the plasma wave system and the magnetometer, precisely the 2 instruments that are generating the density map and the magnetic field record that 2026 papers are still being published about. A carefully planned power management procedure, internally nicknamed the Big Bang by the engineering team at NASA's Jet Propulsion Laboratory, is being tested on Voyager 2 during the summer of 2026, with the goal of replacing several older, power-hungry components with configurations that draw less electricity. If those tests on Voyager 2 succeed, the same procedure will be attempted on Voyager 1 no earlier than July 2026. If the Big Bang works as intended on both spacecraft, it could extend their operational lives into the 2030s, keeping the plasma wave system running long enough to add another 8 to 10 years of continuous density measurements to the map that has been building since 2012. Every additional year of data means another 3.6 astronomical units of interstellar space sampled at the level of detail that no other instrument can provide. By 2030, if Voyager 1 is still operating, the map will extend approximately 65 astronomical units beyond the heliopause, covering a significant fraction of the region. Scientists believe forms the very local bubble of interstellar space surrounding our solar system. And that map is already actively being used. The density measurements are not just sitting in an archive waiting for someone to eventually write a history of the mission. They are feeding directly into current, active NASA science. IMAP, the Interstellar Mapping and Acceleration Probe, which launched in 2024 and is now operating at the first Lagrange point between Earth and the Sun, studies the heliosphere's outer boundaries by detecting energetic neutral atoms, particles produced at the boundaries that travel inward without being deflected by magnetic fields. To correctly interpret what those particles are telling IMAP about the heliosphere's shape, size, and boundaries, scientists need ground truth data about the actual properties of the interstellar medium on the other side of those boundaries. The density map Voyager 1 has been building is that ground truth. Without it, IMAP's measurements would be harder to calibrate and interpret. With it, the 2 missions work in concert, IMAP measuring the heliosphere from the inside, and Voyager 1 mapping the interstellar medium on the other side, together building a far more complete picture of the heliosphere-interstellar medium interaction than either mission could produce alone. A separate 2025 paper by Cummings and colleagues, noted in a 2026 ARCHIV study on cosmic ray propagation, reported another piece of what Voyager's dataset makes possible. By measuring galactic cosmic rays in the very local interstellar medium from inside it, Voyager 1 provides the first direct view of the low-energy cosmic ray spectrum at the source, uncontaminated by the modulating effects of the solar wind that distort every cosmic ray measurement made inside the heliosphere. The 2026 ARCHIV paper used those Voyager 1 cosmic ray measurements as a ground truth dataset to test models of cosmic ray propagation through the galaxy, finding that they favor models in which there are no significant cosmic ray sources within roughly 150 to 200 parsecs of our solar system. 1 parsec is about 3.26 light years. So this is saying that the nearest dominant contributors to the low-energy cosmic rays streaming past Voyager 1 right now are coming from sources at least 490 to 650 light years away. That conclusion could only be reached using Voyager 1's direct in situ cosmic ray measurements from outside the heliosphere. It is another piece of the map nobody asked for, another layer of the interstellar environment being documented by a spacecraft that was supposed to have finished its job 3 decades ago. The phrase that Ocker used when the 2021 Nature Astronomy paper was published captures the spirit of this entire story better than any summary. She said that Voyager had given scientists a new way to explore the interstellar medium, one that did not depend on waiting for rare shockwave events but was always on, always running, always measuring. And Gurnett, in the PNAS profile published that same year, said that if he had to guess what would happen to the density as Voyager moved further from the heliopause, he would predict it would reach a peak and then come back down, possibly indicating that interstellar material is piling up near the heliopause like snow in front of a snowplow. That is the kind of prediction that can only be tested by a spacecraft that is actually out there, still running, still measuring, adding new data points to the map nobody in 1977 planned to create. Still measuring the electron density of the space between stars, still adding data points to a map that stretches from 0 astronomical units beyond the heliopause in 2012 all the way to 46 and counting in 2026. Nobody asked it to draw this map. Nobody programmed it to do this specific job. It just happened to have exactly the right instrument in exactly the right place at exactly the right time, and the universe provided the signal. Subscribe now to follow every major update from this mission, as the Big Bang power management upgrade is carefully attempted on Voyager 1 later this year, and as researchers around the world continue analyzing the continuous density map being built, one faint electromagnetic plasma oscillation at a time from 25 billion kilometers away across a signal gap that takes 23 hours at the speed of light just to cross. Drop a comment telling me what hit you hardest in this story. The fact that scientists discovered the continuous density signal not at the time of launch or the heliopause crossing, but by going back through the already archived data years later and finding something nobody had been specifically looking for. The density rising 40-fold after the heliopause crossing. The fact that this unasked-for map is currently the most detailed in situ measurement of the interstellar medium ever obtained anywhere by any instrument. The cosmic ray finding, placing the nearest major galactic sources at least 490 light-years away. Or the sheer improbability of a spacecraft launched in 1977 to study Jupiter and Saturn, quietly becoming the most important astronomical mapping instrument in the history of human spaceflight without ever being asked to do so. Thanks so much for watching all the way through to the very end. I will see you in the next one.